Hello everyone, this is Mohammed Sarfaraz. I am an assistant professor in a mechanical department in Engineering College, Chalawar. Today we are going to discuss about the subject power generation. It's a 8th semester subject. Our subject code is 8ME3A. So in this lecture, we were going to discuss about the British cycle or Westerman cycle. So let's discuss about this. So here we were discussing about the open cycle gas turbine power plant. As I already told you, what is mainly the most of the power gas turbine power plant are open cycle gas turbine power plant because there are various advantages open cycle gas turbine power plant over the closed cycle gas turbine power plant. And the main thing is that it's a as I told you what is open cycle gas turbine power plant in this type of turbine power plant. We are using fresh air and for the cycle, and after exhausting the turbine we are not reusing this air, so that's the open cycle gas turbine power plant. So here we are discussing about the basic cycle, or we can say that figure schematic diagram or figure of this gas turbine power plant. Here the main three components are there: compressor and compression chamber and the turbine. You can see the compressor and the turbine are coupled together, right? So as I have already told you that whatever the power we are producing by the turbine, 66% of the power we are using for driving this compressor. That's why this type of cycle having very low efficiency is there. So in this cycle we can see that first is phase here, we are entering the compressor, and this after the compressing this air, we are sending this air into the combustion chamber, where we are adding fuel. After the this air and fuel is combined and combustion taking place, and due to this combustion hot gases are there, and these hot gases are fed into the turbine, and where expansion is taking place, and due to the expansion of these hot gases, turbine rotation start, and through the turbine, as we know that the generator and armature generator are there in the turbine. When the turbine rotates, shaft rotated, and the shaft rotates, generator armature rotated, and generator generated electricity, and this electricity is used for various purposes. And after this expansion gases, exhaust gases are there, which is directly exhaust into atmosphere in an open cycle gas turbine cycle. So here is a PV and TS diagram of Brayton cycle, and we can say that open cycle gas turbine cycle. You can see this is the idle cycle, obviously, because nothing is practical cases, nothing nowhere asymptotic process taking place. That's why this idle cycle, this is PV and TS diagram. First of all, let's see the TS diagram. We know that it's a power generating cycle. That's why it's a clockwise cycle, as we already know about the clockwise cycle and anti-clockwise cycle. So it consists of mainly four processes. 1 to 2 is a isentropic compression process. That's isentropic means no entropy changes, but it's not practical. That's why it's idle cycle. So 1 to 2 is a isentropic compression process. As in a PV diagram, we can see 1 to 2 the volume is decreasing because compression taking place, and 2 to 3 is a heat generation process which is taking place in a, as we know that it's a constant pressure process, constant pressure heat addition process. That heat addition is taking place in a combustion chamber, right? So next is Thesis-4. Thesis-4 is a isentropic expansion process, and when the expansion is taking place in the turbine. So when the expansion is taking place, the volume will be increased. So in a PV diagram, you can see that Thesis-4 is isentropic process, but volume increases. And force 1 is a constant pressure heat reduction process, right? So heat reduction, you can see 4 to 1 heat reduction process. That's the constant pressure, right? So here we completed that Brayton cycle, and next we are going to discuss about entropy. What is entropy? As you already know that is a degree of induction or change of indifference. It's a very important parameter I measurement which is used to calculate the efficiency of the turbine, and the unit of this entropy is joule per Kelvin. And there are various processes due to the entropy increases, whether due to external interaction and due to internal change in the system, as you know that. And according to the second law, is based on the second law of thermodynamics, as you know that ds is del Q by T. So there is a various method of improving the thermal efficiency of a cycle cycle. There is, as we already told you, in a Rankine cycle, there is a 3 method: process, regeneration, reheating, and intercooler. We'll discuss about detail about these 3 methods are there. First, regeneration. What is regeneration? In a figure, in a pictorial view, you can understand that what regeneration is there. That is, here we are using heat exchanger. So, in a regeneration as a figure, as you know that from 5 days to 6, that's a exhaust gases for turbine. We are using this heat to generate to heat. We are using this heat to heat exchanger to heat the inlet air which enter into the combustion chamber. So due to this, what will happen? The first thing is the entering air heat point. The air will be less. Air will be hot. That's why it will be require less fuel, right? They can use the heat coming from the compressor, thereby reducing the mass of the fuel supplied in the combustion chamber. So it's a method of improving efficiency. That's why that's a regeneration. And the next is reheating. You can understand by its name reheating. Heating. That's a we are using 2 types of turbine is there. First is high pressure turbine and low pressure turbine, and compressor. These all are covered in the same shaft. So after compressor, that compressor chamber 1 and the heating and exhaustion taking place in work is after exhausting these gases to the high pressure turbine. This is fed into the second combustion chamber. That's also called reheater. After that, the temperature increases of the gases and the low pressure this is fed into low pressure turbine. As we know that it's a efficiency depends on the temperature, that to temperature inlet exhaust, and due to this after 0.5 the temperature is increases, and due to this high efficiency is increases, high power is generated. So high pressure turbine drive the compressor and the low pressure turbine provide useful power output. As we can see here in the diagram, this high pressure turbine is useful for the compressor. So and power is generated by low pressure turbine. And the next method is intercooling. As you know that this is basically used for reducing the compressor work, because as you know that allows most of the part of this work is used by the compressor. That's why if we reduce the compressor work, then we can increase the overall efficiency. So right, compressors and gas chamber turbine utilize the major percentage of the power developed by the gas turbine. As we see here, that here we are using some intercooler between the high pressure and low pressure turbine. Due to this, the air into the high pressure, it somehow reduces heat up. So that's why it increases the work output, and the work required by the compressor can reduce the compressing the air in 2 stages in compression intercooler between the 2 stages, you can see. So here we are going to end about this gas turbine cycle or Brayton cycle. So hope you understand about the basic method of improving the efficiency of the gas turbine cycle. So thanks for the lecture. We'll continue in the next lecture. Thank you.